Okay, think about the world around you for a second. The screen you're looking at right now, the windows in your room, even a medical implant that's designed to go inside a human body, there's this invisible revolution happening on all of them. It's a technology that coats our world in layers that are, get this, just a single atom thick. It's happening all around us, so let's pull back the curtain and see exactly how it works.
So what's the connection here? I mean, what kind of technology could possibly link something like a delicate biomedical implant with something as tough as concrete? Or as futuristic as a smart window that changes with the heat? You know, on the surface, they seem like they're from totally different worlds.
Well, the answer is literally on the surface. We're talking about advanced, ultra-thin coatings. And no, this isn't like a can of spray paint. These are microscopic layers engineered with unbelievable precision that give normal objects these incredible new powers. This is what engineering a surface, atom by atom, really looks like.
But why this obsession with perfection? Why does every single atom have to be in just the right place? Well, it's because the tech of the future, think flexible electronics, super efficient solar panels, it all depends on coatings that are absolutely flawless. The old ways of doing things, they just can't cut it anymore.
And this slide really lays out the challenge. You know, conventional coating methods, they often use a ton of heat, which can totally wreck sensitive materials. The coatings themselves can be uneven, kind of patchy, and they just don't stick that well. But modern tech, it needs the complete opposite. You need to be able to apply these coatings at low temperatures, they have to be incredibly durable, and you need what's called perfect conformality, which is just a fancy way of saying the coating has to perfectly cover every last microscopic nook and cranny, no exceptions.
So how on earth do you get that kind of perfection? Well, the first technique we're going to look at is just incredible. It's so precise, it's like you're literally painting with individual atoms. It's called Atomic Layer Deposition, or just ALD for short.
The magic phrase here is self-limiting. What that means is that each step in the chemical reaction naturally just stops once one perfect layer of atoms is down. You literally can't add too much. It's like it has a built-in off switch. And that right there is the secret to its insane level of control.
The whole thing is this really elegant four-step dance. First, you introduce one chemical, and it sticks to the surface. Step 2, you flush out any of the extra stuff that's just floating around. Then, step 3, you bring in a second chemical that reacts with that first layer. And finally, step 4, you flush everything out again. That's it. One cycle, one perfect atomic layer. You just repeat that dance over and over and over to build up your film.
So where does this show up in the real world? How about this? Biomedical implants. Some are made from a material called zirconia, which can have these teeny, tiny microcracks. You can't fix them with high heat because that would damage the implant. But with room temperature ALD, scientists can actually send chemicals deep inside those cracks to seal them, atom by atom. It's not just a coating, it's like healing the material from the inside out. Amazing.
Okay, but what if your material is super sensitive to any kind of heat? How do you apply a really tough, high-quality coating then? Well, for that, you need to bring in the big guns, a plasma-powered solution called PECVD.
PECVD is a really clever trick. The secret ingredient here is plasma. You can think of it as a super-energized gas, kind of like a lightning bolt in a bottle. This plasma gives the chemicals all the energy they need to react and form a coating without you having to crank up the furnace. It's basically a chemical shortcut that lets you do amazing things at much cooler temperatures.
And a fantastic example is smart windows, the kind that can change their tint when it gets hot outside. To make these, PECVD deposits these incredibly thin, alternating layers of different materials. One layer bends light a lot, the next bends it just a little. And it's this precise stacking of layers that gives the window its smart ability to control heat and light. It saves energy, and, let's be honest, it just looks really cool. Now, not all of these advanced coatings start out as a gas in some fancy vacuum chamber. Our next technique actually starts as a liquid. It's called the sol gel method, and it's kind of like creating liquid armor that then solidifies into a powerful protective shield. It's a pretty wild transformation. You start with this chemical soup called a sol, and over time, the molecules start linking up, almost like a spider web forming, and it turns into a gel. You can then spread this gel onto a surface, and after it dries, it turns into this hard, durable, super thin film with whatever properties you designed it to have. And this isn't just for delicate lab equipment. Think about concrete. Yep, boring old concrete. By applying a specific sol gel coating, you can make the surface hydrophobic, which means it totally repels water, and you also make it way more durable, protecting it from wear and tear. It's a pretty simple idea with a huge real-world impact.
All right, so we've got atomic precision with ALD, low temperature toughness with PECVD, and liquid armor from the Sol gel method. Each one is really powerful on its own, but the true breakthrough, the real cutting-edge stuff, is when scientists stop using them one by one and start combining them.
And this, right here, this is the key. The future isn't about picking one of these methods. It's about building hybrid systems that take the best parts of each one to create coatings and materials with abilities that would have sounded like pure science fiction just a few years ago.
When you combine these techniques, you get these massive advantages. You can build up complex stacks of different materials without ever letting air touch them, which means no contamination. You can combine, say, the super hardness of one material with the electrical conductivity of another. A perfect example is integrating two different systems, like PVD and CVD. It lets researchers lay down a layer of metal and then immediately, in the same pristine environment, grow a perfect layer of graphene right on top. That's a total game changer.
So, what does this all mean for us, really? It means the future is coded. The surfaces of tomorrow aren't going to be just passive things we touch. They're going to be active, they're going to be functional, they're going to be intelligent, all thanks to these incredible technologies. And where is this all going? Well, we're looking at much more efficient solar panels, biomedical implants that don't just sit there but actually help the body heal and integrate. We're talking about electronics you can literally fold up and put in your pocket. Imagine a building or a car with a surface that can clean itself or even heal itself from a scratch. That's the future these coatings are making possible. You know, in the end, it really boils down to this quote. As one source puts it, understanding these processes is absolutely vital. As our technology demands more and more from our materials, the ability to design things atom by atom, well, it's not just a nice bonus anymore. It's the only way forward.
So this is where we're at. For really the first time in human history, we can build our world from the atom up. We can give almost any object new, incredible properties. The question isn't, can we do it anymore? The question now is, what are we going to build? And what seemingly impossible problems are we finally going to solve?